Hello, this is Mr. Gilmore with the 2.5 Part 1, the Proofs of the Fundamental Angle Relationships lesson. Now, today we're going to prove our very first set of geometrical theorems. And as you can see, this is just Part 1. We will finish this set of these geometrical theorems in the Part 2 lesson. Now, before we get into proving these first set of theorems, what I'd like to talk about or really introduce is another way or another format of organizing our proof. So we're going to be introducing what's called a column proof. So we've experienced flowchart proof, but what we're going to do is transition into a column proof. And here's the reason why. Flowchart is really good at showing us how the logic is all connected and how it flows from one statement into another. However, it can get disastrously messy because with all the statements we make and with all the arrows we must make with connecting our thoughts together, it can get quite cluttered and very messy very fast. So we're going to begin to organize our proofs into a column proof. So what is a column proof? A column proof will have two columns. The first column is where we're going to make the statements. These are what is going to take us from the given to the conclusion. And the second column is where we'll find our justifications to the statements, or in other words, our reasonings. In the reasons column, you're going to find our definitions, our postulates, and previously proven theorems. Now, one thing that we can do in a column proof, which you will see that I have done in some of my column proofs, is that if a statement has the same reason, so if I should say if statements, so if I have two or more statements that have the same reason back to back, then they may be written on the same line. And you'll see an example of that in the two column proof. So with that, let's jump into our first set of geometrical theorems. This is actually one of the fundamental angle relationships. However, you should recognize this. We have already proven the linear pairs theorem. We proved it with a flow chart. Now, what we'll see is in our proof of linear pairs theorem, it will be the exact same statements and the exact same reasons that we made in the flowchart. However, it's going to be more organized. It will be in our column format. So before we get to our column format, again, let's set up the linear pairs theorem. Basically, the conditional says that all linear pairs are supplementary. Or if we read it as an if-then statement, it would say if two angles form a linear pair, then they are supplementary. So we're given an angle 1 and angle 2 form a linear pair. We have our diagram, and we're going to prove that angle 1 and angle 2 are supplementary. Now, I would suggest to make sure that you write this diagram down, because on the next slide, we're going to see only the column proof, and we're going to lose our given proof statements, and we're going to lose our diagram. So I would suggest you have that diagram written down so you can follow along with it in front of you. This is the linear pairs theorem proof organized into a two column. Now, if we were in class, I would have walked through this step by step, just like I would have done with the flowchart proof. However, it's much better organized here in this table for you, and you can see it all written out virtually. So let's follow through with the logic. In our first statement, we're given that two angles form a linear pair. Well, by the definition of linear pair, there's really two things happening. The first thing I know about those two angles is that they are adjacent. So I follow with that first thought. And in step 3, you see, I'm following with the thought of because they are adjacent, there must be a ray, BD, that passes through the interior of the angle ABC. That's by the definition of adjacent. Well, following through with a ray passing through the interior, we can then imply that the sum of the two subangles, or in other words, angle 1 and angle 2, they will add to the whole angle, angle ABC, with the angle addition postulate. Now, that's as far as I can take that first thought, with knowing that because the two angles form a linear pair, that they're adjacent. But there's another part to the definition of linear pair. It says that their non-common sides form a line. So in step 5, you see me following with that next thought. I state that the rays BA and BC form a line. That's the definition of linear pair. That's where I get that from. I reason my implication statement there. Well, what follows then from two rays forming a line? That means they form a straight angle. So in statement 6, angle ABC is a straight angle Why? Because it satisfies the definition of straight angle. That means I can call the measure of angle ABC 180 degrees by the straight angle postulate. Now, this is where it gets interesting. I'm going to connect two statements together to form another new statement here for step 8. See, if we look back at step 4, or statement 4, it says that the measure of angle 1 plus the measure of angle 2 equals the measure of angle ABC. But in step 7, we stated the measure of angle ABC is 180 degrees. Well, what does that mean? That means we can replace the measure of angle ABC with 180 degrees. Or in other words, the sum of the angles is equal to the whole, and the whole is equal to 180 degrees, which means by the transitivity property, we know that the measure of angle 1 plus the measure of angle 2 equals 180 degrees. What does that mean for our angles? If we have two angles that add to 180, we call them supplementary, and that's by the definition of supplementary. And so these are really the exact same statements that we saw with the flow chart, but now they're nice and organized into this two-column format. Let's take a look at another one of our fundamental angle relationships. I like to call this proof the T theorem, because in our diagram, it looks like a T, or an upside down T at that. Here's what it states. If two angles of equal measure form a linear pair, then each is right. So now we have a diagram here where we have labeled two angles that do form a linear pair, and we've marked each of them as being equal to each other. Now notice that I didn't put the right angle marker in there. I didn't put the right angle marker in there because I'm going to prove they're right angles. So I don't know they're right angles right now, but I'm going to show that they are, or demonstrate that they are right angles. So in our given statement, I'm saying that angles 1 and 2 form a linear pair, and they're equal to each other. They're equal in measure to each other. We're going to prove that angles 1 and 2 are right. Now, here's what's going to be beautiful about this proof. We just proved the linear pairs theorem. What that means is the linear pairs theorem is now a tool that we can use. Whenever we encounter a linear pair, we can point at it and call it supplementary. Well, here in the T theorem, we've just encountered a linear pair. Angle 1 and angle 2 form a linear pair. So you're going to see in the proof of the T theorem that right out of the gates, we're going to use the linear pairs theorem to help us prove the T theorem. And we can do that. We can use previously proven theorems now as reasons in our reason column. Here is the two-column proof of the T theorem. Now, of course, in class, I would have gone through this step by step, but I'm going to actually read through the steps and explain where they come from. So obviously, statement 1, we know that was the given. We know that angle 1 and angle 2 form a linear pair and that they're equal in measure. But look at this, step 2. Since I know angle 1 and angle 2 form a linear pair, I can call angle 1 and angle 2 supplementary. Why? By the linear pairs theorem. We've already proven that, so let's use it. I don't want to go back through and show that they're supplementary again. I've already done that, which means I'm going to use the linear pair theorem in the progress to help prove the T theorem. So now in statement 2, if I've got these two angles as supplementary, I can state in statement 3 that the sum of the two angles adds to 180 degrees. That comes from the definition of supplementary. Now, this is where I have the example of I have two statements now that are going to follow from statement 3. And those two statements actually use the same reason, which means I'm able to put the two reasons on the same line, the two statements on the same line. So in statement 4, what I'm doing from statement 3 is I'm going to replace the measure of angle 2 with the measure of angle 1. I can do that because I know that from my given that the measure of angle 1 is equal to the measure of angle 2. So my first statement in statement 4 is the measure of angle 1 plus the measure of angle 1 equals 180 degrees. That's substitution. But notice my second statement is me simplifying the equation. The measure of angle 1 plus measure of angle 1 really is 2 times the measure of angle 1, and that equals 180 degrees. That is by substitution again. So again, I'm allowed to combine statements that, consecutive statements that use the same reason into the same line. Now, what follows from knowing that 2 times measuring 1 equals 180? I can use the division property in statement 5 to divide both sides by 2, because I want to prove to you that measure angle 1 is a right angle. Well, then in statement 6, when I reduce my statement from statement 5 using substitution there, then I've now proven that the measure angle 1 is equal to 90 degrees. And whenever we simplify, that's just substitution. Okay, so that's why my reason in number 6 is just substitution. Well, I already know that measure angle 1 and measure angle 2 are equal, which means in statement 7, I can declare the measure angle 2 equal to 90 degrees. Because if angle 1 is equal to 90 and 1 is equal to 2, that means by transitivity of equality, angle 2 is also equal to 90 degrees. Now from statement 6 and 7, I have both angles declared as right angles, or sorry, 90-degree angles, which means in statement 8, I can declare angle 1 and angle 2 are right angles by the definition of right. And that is our proof of the T-theorem. So what does that mean? We now have two theorems in our toolbox. We have the linear pairs theorem and we have the T-theorem, which means if I ever encounter a pair of equal angles that form a linear pair, then I can call them both right angles. And we actually use the T-theorem here and there. You'll see it comes in handy along the way. Let's take a look at one more theorem for today's lesson. This one's known as the complement theorem. Okay, the complement theorem, because what we're going to prove is we're going to prove that two angles are complementary. Here's what the conditional states. If the non-common sides of two adjacent angles form a right angle, then the angles are complementary. Let's take a look at the diagram. In the diagram, I have a pair of adjacent angles in which their non-common sides form a right angle. And I've labeled each of my rays so that I can actually name the angles. So take a look at the given. Angle ABD and CBD are adjacent, right? And that's what our conditional states in the given. And I went ahead and stated that ray BA and ray BC form the right angle ABC. What we're going to prove is that angle ABD and angle CBD are complementary. In other words, we're going to show that the sum of angle ABD plus the angle DBC is equal to 90 degrees. I have again used the two-column format. Let's take a look at this. So this one's not a very long proof. As you can see, we can reach our conclusion pretty quickly. In statement 1, we have our given listed out where we've listed our two angles that are adjacent, and we have the two rays that form the right angle. Well, I'm going to go with the first thought of knowing that the two angles are adjacent. So you see in step 2, or statement 2, I'm going to state that I have a ray, BD, that passes through the interior of my angle ABC. That is by the definition of adjacent, right? Because if two angles are adjacent, they have this common ray, thus that ray passes through their interior. Why is that important? Because now I know in statement 3 that the sum of the two subangles, angle ABD and CBD, add to the whole angle the measure of angle ABC. That's angle addition postulate, which I have listed as AAP. Now again, that's really all I can do with the first thought is kind of reach the end of that first thought, but there's still something else in the given. Rays BA and BC form a right angle. Well, that means I know what the measure of that angle is. Since they form the angle ABC in statement 4, I can say the measure of angle ABC is 90 degrees because that flows right from the definition of right angle. Well, look at statement 3 and statement 4. We're going to combine statement 3 and statement 4 to make a new statement for statement 5. The sum of the angles ABD plus angle CBD is equal to the measure of angle ABC, and in statement 4, the measure of angle ABC is 90 degrees, which means by the transitivity property, I can say that the sum of the two angles is equal to 90 degrees, right? Because they're equal, right? I'm basically following from the transitivity property. The sum is equal to the whole, and the whole is equal to 90, which means the sum is equal to 90. Hey, now in statement 5, I am saying that the two angles add the 90 degrees, which is what I wanted to prove. I wanted to show that they add 90 degrees because now I can call them complementary angles. So in statement 6, angles ABD and CBD are complementary. Why? Because they satisfy the definition of complementary. So that means we have added the complement theorem now to our list of theorems or a list of tools that we can use for future proofs. Yes, we are allowed to use theorems to help us prove other theorems. And that's why there is actually an order to why we've seen these theorems in this order, because you're going to see some theorems in the next lesson. They're going to help us to prove some other theorems. This is the end of the 2.5 part 1 lesson on the proofs of the fundamental angle relationships. We'll continue to look at the next set, or really to complete the set of the fundamental angle relationships in the next lesson, the 2.5 part 2 lesson. If you do have any questions about these proofs, do not hesitate to email me. I'll get back to you. With that, be good and do good.